has adverse thermal-hydraulic conditions and support structure unable to control the resulting vibration.
Correct.
And so part of the, I don't know if it's part or all, of the action that you're using to justify operating at 70% power is the actual power reduction, and you're no longer worried about the support structure performing a design function that it was never intended to perform, which is in-plane stability for those tubes, or you still need to rely on some support in the in-plane direction to prevent FEI occurring.
Okay. And we'll address that as we go forward. Let me talk for a minute about the role of thermal-hydraulic code. In previous meetings, we've talked about the conclusion that MHI's thermal-hydraulic code underpredicted the thermal hydraulics and effectively showed more margin to the out-of-plane vibration phenomena than actually existed. Just real quickly, the thermal-hydraulic code, the second block on my little diagram here, I've made a simple diagram. You start with operating conditions. The thermal-hydraulic code analyzes and models the conditions inside the steam generator the tubes are exposed to. That then feeds both the structural and structural vibration model and tube wear models. So the key here is starting with reasonably accurate thermal-hydraulic predictions from the code. The code that MHI used, FIT 3, was used in the design of our replacement steam generators back in 2005, 2006, had been in use for 15 or so years by MHI and their other steam generator designs. And in our case, it underpredicted the critical thermal hydraulic conditions, specifically the fluid velocity and the void fraction. As we've talked earlier, the fluid velocity excites the tubes. The void fraction or steam quality is what helps dampen the movement and helps the support structure be more effective through the squeeze film damping. Because of that underprediction, they didn't recognize the lack of margin to the vibration phenomena. Today's work, the US industry typically uses a code called AETHOS, which has been around for a number of years, developed by the EPRI group, the Electric Power Research Institute. As we run AETHOS today on the replacement steam generators, it predicts much more adverse thermal hydraulic conditions, higher velocities, higher void fractions. All the analysis we've done to support the Unit 2 restart relies on AETHOS, not the FIT 3 code, which was part of the problem that MHI had in their design phase in not recognizing this vulnerability. And we didn't rely just on MHI running AETHOS or Southern California Edison running AETHOS. We've had AETHOS run independently by Areva and Westinghouse, who also design and build steam generators. And we've had Areva run a separate proprietary thermal hydraulic code. All of those get very good correlated results with AETHOS today and show more severe conditions than FIT 3 predicted.
Mr. Paul, so yes, so AETHOS shows more severe conditions, but the results from AETHOS also ultimately resulted in stability ratios that were satisfactory. Is that not correct?
In MHI's work, it's even using AETHOS predictions today, and the key is assuming the support structure is effective, showed stability ratios just under 1 in some cases, which is acceptable. Okay? Not, 1.0 would be the cutoff to acceptable and unacceptable. Greater than 1 would be unacceptable. But the key is that assumes the support structure is effective. So clearly, the support structure is a significant element of what did not work effectively in this steam generator design.
So given that, you are going to explain how, at least, or reference that the Cal response addresses the role of either a design change or modifications or other fixes to the support structure to justify operating at 70% power.
The Cal response discusses 70% power showing the thermal hydraulics are acceptable, and in Unit 2 the support structure is acceptable at that lower power level. Okay. Again, you have significantly less fluid velocity at 70% compared to 100%, and I'll show you a schematic in a minute that shows that, and you have a significantly lower void fraction, which means much better damping by both the fluid and the supports in Unit 2. And the Cal response does address that specifically.
Yeah, it would be helpful if you could address at least an overview of how it is addressed. I mean, I know you can't go into all the details in the operational assessment, but at least you can give us a sense, whether this is a calculational methodology, a new methodology.
If you'd hold that, let me get through the upcoming slides, and then I'll come back to that question about how we treated the support structure in the operational assessments, because it was treated explicitly in the operational assessment we did in one case.
Mr. Palmisano. I had one other question. You indicated that Fit 3 has been used by MHI for approximately for 15 years, and I assume you mean successfully, or
Yes.
by that, but that it underpredicted in your case it underpredicted the thermal hydraulic conditions. Could you speak to why, in your case, it underpredicted that, whereas it apparently?
For our specific, yes, I can. For our specific case, Fit 3, this gets fairly detailed. Our replacement steam generators have a triangular tube pitch design. Previous MHI designs that Fit 3 was based on had what's called a square array design. So there's a physical difference in the way the tubes are configured, those 10,000 or so tubes in each steam generator. So Fit 3 had to be modified to model the triangular tube pitch design. There's also, under the US ASME, Associated Mechanical Engineers Code, tells you certain dimensions to use in your calculations. Fit 3 did not take those dimensions correctly. And that was not an input error by a person, that was embedded in how the code was built. So Fit 3 had some problems in how they modeled the triangular pitch steam generators and the values that the US ASME code required that resulted in an undercalculation of velocity. So that, in a summary level, is what occurred with Fit 3 that caused the underprediction to occur.
And had they modeled other steam generators that used a triangular pitch code or pitch as well, or?
I believe they had. They've originally started with square pitch. I believe they've done other triangular pitch steam generators overseas, but with, quite frankly, smaller steam generators with less severe thermal hydraulics. So I suspect even if an error occurred, it was not a significant contributor to a problem.
Could you describe again where you talk about the ATHOS verification done as compared to Fit 3 verification, why there should be have more confidence in ATHOS as compared to Fit 3?
Certainly. So first of all, ATHOS was developed by the Electric Power Research Institute a number of years ago, and a code like that is verified against experimental data. So well beyond our use at San Onofre, the code is written, and then test data is taken off of experimental test loops where they mock up portions of steam generators and actually measure parameters. Then they model that test loop with the code and say, does the code predict with reasonable accuracy what I actually measure? So that's how a code like ATHOS is originally developed and validated. So it's a validated code. What we did, as we looked at this problem, we said, let's have MHI and us run ATHOS and look at the conditions. And the ATHOS conditions came out more severe than the Fit 3 conditions that were done during the design phase in 2005, 2006. To not just rely on that, we had Arriva run ATHOS, their own version of ATHOS, and confirm the calculations MHI was getting with ATHOS, the more severe calculations. We then had Westinghouse, who has a proprietary version of ATHOS, do that as well. So we've had Arriva and Westinghouse run ATHOS independently from MHI and coming up with similar answers out of the ATHOS code. And Arriva also uses a proprietary code called Kafka. They also ran Kafka and have results in a similar range as ATHOS. So we've done some extensive work here to independently run ATHOS to confirm what MHI's calculations are with ATHOS.
Okay.
Hey, Tom, just one other. We mentioned the Fit 3 code was modified because of the going from square pitch, which Fit 3 usually used, to a triangular pitch. My understanding also is these codes, the ATHOS codes, as well as the MHI, are really based on out-of-plane vibration. They don't really look at in-plane vibration because it's assumed it's not going to occur if out-of-plane is prevented. So that appears. Can you explain how the codes had to be modified to model the in-plane vibration?
I think what you're talking about, the thermal hydraulics are done independent of what vibration mode you're talking about. So as we talk Fit 3, it calculates velocity, void fractions, hydrodynamic pressure. It is independent of what vibration phenomena. I think what you're talking about is these downstream models that look at the particular vibration modes and then the wear models.
Right,
again, up until this point, industry experience, and this is not just MHI, this is the under vendors as well, had basically modeled and analyzed for out-of-plane vibration, and if that was acceptable, their experience was there was significant margin to in-plane vibration and was not explicitly analyzed. Okay, so let me move on to corrective actions.
Yep.
So preventing fluid elastic instability, we've talked quite a bit about the role at 100% power, the velocity of the fluid, that's what transfers the energy to the tube. We've also talked about you need to improve tube damping. And this is a function, here's where the support structure comes into play. So this is a function of the dryness of the steam around the tubes and the supports. And the fluid, if you will, the water-steam mixture dampens in a couple ways. One is just physically the tube, if it's moving through an area of steam that has largely water, a low void fraction, is damped more effectively from physical motion than through a very dry area of very dry steam with very little moisture. Secondly, the more moisture, lower void fraction, you have a film of water between the tube and the support. Even if there isn't a strong contact force, that very film of water with the tube moving across the support provides damping. So that's the role of the damping. So my second bullet there, the fluid interaction with the tube, it's a function of void fraction or steam quality, how dry the steam is. So as we look at then how to prevent this from the Unit 3 phenomena from occurring in Unit 2, it's a matter we need to reduce the velocity, we need to reduce or improve the void fraction and steam quality, which results in improvement in tube damping. So the sum total of that, it's less energy input in the tube, causing the tube to start to move, and is better damping that prevents the tube from vibrating excessively. So let me show you very specifically. I'm going to start with void fraction, then I'm going to move on to velocity. So this chart, this is actual data out of Unit 3. See, the blue bar is the number 3 Echo 88 steam generator, and the yellow bar is the 3 Echo 89. On my graph here at the bottom is maximum void fraction. So the higher numbers mean very dry steam. So I talk void fraction or steam quality, calculated a little differently, but either one is a measure of how dry the steam is. On the vertical axis, the number of tubes that were actually damaged due to tube-to-tube wear in Unit 3. You can see that all the tubes that experienced tube-to-tube wear damage were above 99% or 0.99 void fraction. This area, very high void fraction, very dry steam, very little water. Okay? If I then look at the effective power level, and this is all at 100% power. If I look at power level, I took a little different look at this. So on my horizontal axis, it's the same maximum void fraction. And on the vertical axis, it's the percent of tubes exposed to that high void fraction. And my green line on the graph is at 100% power. What this tells you, that peak there on the far right on that green line, slightly over 30% of the tubes at 100% power were exposed to a 99% void fraction or higher. So that adverse, very high void fraction, the number of tubes in the Unit 3 steam generator is exposed to that void fraction.
Well, Tom, you mentioned that this is the thermohydraulic, phenomena, and all 4 generators are designed the same. Wouldn't this not be representative also of the void fraction for Unit 2 at 100% power?
Yes, it is.
Okay.
In fact, this graph is very representative of Unit 2. Let me back up. The tube damage, this is Unit 3 specifically. Okay. This graph is identical essentially for Unit 3 or Unit 2 because they're the same design, same construction, the thermal hydraulics are the same, which is why early on we concluded Unit 2 is susceptible to the phenomenon. Okay. The yellow line on this graph shows you the effect of reducing power to 70%. The effect on void fraction, again, this is what improves the damping and improves the effectiveness of the existing support structure. There will be no tubes. None of the 20,000 tubes in Unit 2 combined 2 steam generators will be exposed above a 92.5% void fraction. That is a significant reduction in the void fraction and the dryness of the steam with that power level reduction.
Tom, for the void fraction as well as the next slide for that you have for velocities, you were going to talk about comparison between other similar units at 100% power. I didn't see that in your slides.
Would you hold that thought for a minute? Let me get through the slides and I'll come back to that,
Okay.
please. Okay. So the next slide, I've put these two together because I want to show you the actual tubes damaged in Unit 3, the yellow and blue bars, the green line, what was exposed at 100% power, and as was noted by Mr. Lance, that green line would be applicable to Unit 2 or Unit 3, and the effect of a reduction to 70% power, no tubes will be exposed to the void fractions that were part of the cause of the fluid elastic instability, the unstable tube vibration, and the tube-to-tube wear. And that void fraction fundamentally improves the damping, which improves the effectiveness of the support structure for damping.
You've said that a number of times, Mr. Palmisano. I'm just trying to understand how it proves that. Could you just big picture tell us how that's demonstrated, either calculationally, by testing, experiment? I'm just trying to understand it. By the models that you've used previously?
In terms of
new
how
models?
how the void fraction improvement occurs?
Right,
Okay.
and how how they demonstrate that improves the dampening? How was that calculated? And then how does that translate to concluding that there will be no tube-to-tube wear?
Okay. First of all, we've got our actual data measured out of Unit 3 that just relates where the damage occurred to the void fractions. Then, how do we correlate a lower void fraction to better damping? That is done calculationally, and those calculations are based on experimental data. The experimental data you referred to in the 2002-2003 timeframe developed the understanding and the equations that relates things like void fraction and fluid velocity to the amount of damping that occurs, the amount of tube excitation that occurs, that would allow the vibration to occur above a critical level of velocity based on its void fraction. It gives you kind of a complicated answer, but we take this data, we go into the calculations that are based on experimental data.
From what the Canadians did in 2002?
Largely the Canadians in 2002 to 2005. Westinghouse has some experience with this from a testing standpoint as well.
But, and I know you said that you're still looking at why, but it's my understanding, based on what you know now, that this was not considered back at the time that steam generators were designed.
The in-plane vibration was not considered. Okay. Again, the paradigm at the time, not just MHI, was that if you had adequate margin to out-of-plane vibration, which occurs at lower levels of velocity, for example, you would have more than enough margin in-plane vibration. Clearly wrong. History has shown, experience has shown that was not a correct paradigm. There were many years by many manufacturers supporting that paradigm. The data from 2002 timeframe, done experimentally, never seen in practice, and again, we've talked to more than one steam generator designer who confirmed that mindset, if you will. Okay? But again, to answer your specific question, the calculation of the improvement of damping with void fraction is done calculationally, but it's based on experimental data and real measurements.
And this was new work, I mean, as it applies to actual steam generators? Or has this been done?
Well, the research that's been done since 2002 is
Right.
related to steam generators.
Right.
I think you're familiar with Dr. Michelle Pettigrew, who we brought in,
Right.
authored a number of that, ran a number of the experiments, working quite a bit with some steam generator manufacturers. So they were looking at YouTube steam generators.
But the work that was done that went into the operational assessment in this regard, but has that ever been used in the design of other operational steam generators?
I can't speak broadly to the design of other operational steam generators. It is certainly probably a first-time use in operational assessments.
So it represents new work.
It represents new work, as well as the operational assessments we did and submitted as part of the CAL response.
I think what's also important to note is that the return of such a large portion of the tubes to this void fraction level, less than 92.5%, as Tom mentioned, that is very benchmarkable to other plants with U-tube steam generators.
Right.
Other plants we know operate above 90% void fraction, but less than 95% void fraction, and operate there successfully. So it is backed up by other industry experience from the last several years.
Yeah, I was going to get to that was the heart of Mr. Werner's question in terms of, and so as I get through the next couple slides, we'll come back to that. What I want to show you, now this shows you a different look at void fraction. In this case, it's steam quality. The terms are similar. On the left, you see the analysis that shows steam quality, and the red and pink is very severe numbers, relates to high void fractions. This is a cross-section of the steam generators. And on the right side, I show you the analysis at 70% power. You see the blues and greens, which are much lower steam quality values, and they correlate with a reduction in void fraction. I just used the plot for steam quality in this case. If I look at the next slide, I've talked about velocity and void fraction or steam quality is important. This is the look at velocity. Again, at 100%, these are the velocities that occur, and you can see the red and pink, which are the severe numbers, the high velocities. The reduction of 70% significantly reduces the velocity, and again, imparts significantly less energy to the tube.
And Tom, can you just describe how those graphs were created? What model was used for these
They're
graphs?
created out of Athos.
Okay.
So the thermal hydraulic model out of Athos, which we are using currently, which we had run by multiple vendors to ensure the results correlate, that's based on today's Athos calculation
Okay, thank you.
for steam quality and for velocity. So now to come back to Mr. Werner's question about, how does this compare? I think essentially that was the heart of the question. At 100% power, the Song's Unit 3 replacement steam generators and Unit 2 is the same basic thermal hydraulics, certainly from a void fraction standpoint, operated in a range with the 99.5% higher than other steam generators had typically operated in. There had been some in the higher void fraction ranges, as Pete said, but none as high that we're aware of as 99.5%. So clearly, when this design was developed and upsized, it wound up with a void fraction and velocities higher than had been successfully experienced before. Partly because of the underprediction of Fit 3, it was not recognized the lack of margin that created, okay? And that is essentially part of what drove the damage in the Unit 3 steam generators, coupled with the support structure inadequacies. Okay. A reduction to 70% power brings the thermal hydraulics, the void fraction or steam quality and velocities, back within the range that other large U-tube steam generators had operated with successfully. And we've benchmarked that with some other plants through the Electric Power Research Institute.
So what is that value you're looking for the other large steam generators for other units as far as void fraction?
I think we've seen numbers around 95% for a maximum void fraction.
Yeah, in the 90-95% range, and we've got the specifics in the confirmatory action letter response, but roughly in that, other combustion engineering design or modeled pressurized water reactors, those steam generators operate in that 92-94%.
Yeah.
Just so
Void
we're clear,
fraction.
we're talking about local maximum void fraction.
We're talking about
correct.
local maximum
Not
void
averages.
fraction.
That's
This is
correct.
a very localized phenomenon. It's not an average void fraction. It's a localized maximum void fraction, which is your most severe condition. And as Pete said, in the confirmatory action letter response, we've got what's called a spider diagram that shows you at 100% power our operating thermal hydraulic parameters compared to several other plants, and shows you the reduction of 70% brings us back in with the envelope of successful operating experience. And I can take you through the CAL response to show you specifically where that is. And that is thoroughly discussed.
Okay.
Mr. Pomzan, I'm one other question. Earlier, when you talk about the causes, you indicate, that both the high void fraction as well as the high velocities. What I'm seeing that you're focusing on is primarily the void fractions. Is that the main contributor to that, to FEI, or do you have to have both, or can you explain the relationship?
Well, we're focusing on both velocity and void fraction. They're both important. Again, velocity is what excites or puts the energy into the tube. Void fraction is what affects the damping, both by the fluid itself and by the interaction with the fluid and the anti-vibration bar. So velocity is important to how much energy you put into the tube, and void fraction is important to how much damping the tube experiences. So I've talked about void fraction a couple times because it's related to adverse thermal hydraulics but affects the effectiveness of the support structure. So basically think adverse thermal hydraulics, ineffective support structure. By reducing power, I reduce velocity and I reduce void fraction. Both are important, okay? Without putting the equations up, velocity itself relates to hydrodynamic pressure, and in that calculation, velocity is mathematically squared. So velocity has a very dominant effect on the calculation of tube instability. Okay? So the bottom line here is they're both important, they both have to be dealt with. And the 70% power reduction deals with it.
And when you did the comparisons to other plants in the conditions that were operating successfully, your comparisons are for both the
Yes,
velocities and
yes.
void fractions?
Yes,
not just
yes, we did, and again, that's fully described in the CAL response itself.
Just so we're clear, I mean, so the underprediction of the velocity by, by Fit 3 was not recognized, the problem with the model, when it was changed from square pitch to triangular pitch a number of years ago. But the void fraction, even under Fit 3, while not predicting 99.6% was predicting 95%, which was still high.
Correct.
And was a matter of concern back in the 2005 timeframe. And so I know that's still being looked at, but that was a matter of concern, and a number of feasibility studies were conducted to try to lower that void fraction before the steam generators were fabricated. But apparently it was not. So we'll need to understand that better as we go forward.
And we have as well. We've asked MHI for a better explanation of that, and we are looking at that in ourselves because, as you say, the void fraction was high. It was not predicted as high as 99.5%, but it was high, it was questioned. Ultimately, the calculations and the operating experience showed, even with that void fraction, the system should have been effective, and it was not. So clearly that's a failure, several reasons for that failure that have to be dealt with. Okay, operational assessments. So we've built through to how the tubes are moving, why they're vibrating, the fluid elastic instability, the role of the thermal hydraulics, the role of the damping, and the role of the support structure. So, and we're going to talk about corrective actions in a minute, but from a steam generator program, as we get ready to return a steam generator to service after any outage with any inspection, we have to do an operational assessment. Early on tonight, I talked about the backward look, the condition monitoring look to say, did the tubes meet their criteria? Before we restart the plant, we've now got to look forward and say, will the tubes meet their criteria with what I've learned about any wear phenomena or corrosion phenomena as I get ready for the next operating period. So that's the operational assessment. Typically, you do one operational assessment. And there's some standard methodology. There's a couple choices on methodology under the UPRI steam generator program. So as we looked at this, we decided, number one, the typical UPRI program would suffice for the normal random wear we saw, the tube to AVB wear. It would not suffice for the tube to tube wear. The tube to tube wear was a new phenomena. There was really no specific experience with it, with this fluid elastic instability with in-plane vibration, so we simply couldn't do a typical operational assessment. So we really did three different assessments using diverse methods, okay? And I'm going to start from the simple one. We did a traditional operational assessment treating tube to tube wear as a predictable phenomena. And my third bullet, I'll give you, summarizes the results. So we did that. We said that is not sufficient for us. That doesn't give us adequate assurance. It doesn't give us sufficient margin in our minds. So we commissioned Westinghouse to come in entirely independently, no recent history with MHI or our steam generators, and do an operational assessment with their methodology. And they have a lot of experience successfully designing, building, and maintaining steam generators. The third piece, which is probably the most significant and most unique piece, we commissioned Areva to do an operational assessment. And there were two parts to their conclusion.
Hey, Tom, I'm sorry to interrupt. I just want to make sure it's clear what a traditional operational assessment is, right? You do your condition monitoring, you see what wear is on all the tubes, and then you say for this type of wear mechanism, which we know and we can predict the wear rate.
Correct.
Each of these tubes worn so much, they can last so long before you exceed criteria. Right.
Thank you. That is correct. Say a traditional operational assessment would have a known wear phenomena, a predictable wear rate that I can say over the next 22 months, if it continues, no tubes would wear to an acceptable level and challenge steam generator tube integrity.
All right, so
And
that's
based
traditional.
not only by the plant's experience, but by a database of industry experience.
All right, so that's a typical operational assessment that you would normally perform.
And we would, and which we did, but we recognized that tube to tube wear really did not have any operating experience and was a new phenomena and couldn't be simply predicted in the traditional way, which is why we commissioned three different approaches to an operational assessment. With Areva, we took two approaches. We did a very sophisticated approach, and Mr. Howell, this gets to this whole discussion of contact force and gaps between tubes and anti-vibration bars, recognizing that the support structure is an important part of damping and restraining the tubes. So we spent an extensive amount of time with our eddy current data and further testing, identifying contact points between tubes and anti-vibration bars in Unit 2, statistically calculating contact forces across 10,000 tubes and all the anti-vibration bars, 12 contact points on each tube from anti-vibration bars, and then determining, based on the measured data in Unit 2, a statistical analysis of contact force, and we then applied that to say, out of 12 contact points, if 4 are effectively in contact, it sufficiently dampens and restrains the tube. And that is fully described in the Cal response in quite a bit of detail. So that's one approach, and that approach, we set a stability ratio target of 0.75, not 1.0, but 0.75. We did that specifically to make sure we critically and conservatively modeled that steam generator tube bundle and the contact force and the effectiveness of the support structure, and had margin to fluid elastic instability occurring.
So I've read the 60-page summary, and of course it makes reference to the OAs that are this thick, and I haven't gotten through all those, but I will. But this also represents new work, is that?
This is unique. This represents new work, which again is one reason we did 3 diverse methods, because we recognize that this is a significant new body of work, a new approach to this issue, and we know this is something your staff will take some time to understand, and we are prepared to bring in not only our team, but Arriva and MHI to explain the results here. We also challenged this critically. Pete and I have both alluded to these experts we brought in. We set up what we call expert panels. We had multiple challenges all along the way, starting with the concept, starting with is this the phenomena and why, starting with the approach analytically to model this and determine what's acceptable. So we used this panel, including Dr. Michelle Pettigrew, who did all the research on the phenomena, to help us ensure we not only both understood it, but our analysis was an appropriate way to model this and deal with this.
Okay. That would suggest to me, not knowing all the details at this point, that there's still a reliance on contact, at least to some degree, between the AVBs and the tubes, so that the natural frequency of the tubes in the in-plane direction is improved. Is that?
That is true. The operational assessment with a 0.75 stability ratio limit relies on some contact and contact force between anti-vibration bars and tubes. And again, that's fully described as you talked in the 60-page summary and all the supporting documents. The other thing we had Arriva do, as we learned more about the stability ratio calculations, we said if we had no supports effective, none of the anti-vibration bars had any damping contribution, what would the stability ratios be? And for unit 2 at 70% power, the stability ratios in that worst case assumption are less than 1.
So they actually did 2 assessments.
Arriva did 2 assessments effectively. Now, we weren't satisfied with the stability ratio 1, which is why we continued on with the more sophisticated, detailed analysis showing a stability ratio of 0.75.
Okay, so was it like barely less than 1, or?
I'd have to check on the highest value. Again, that's documented in our Cal response. It seems to me it was in the 0.88 range, but I would have to look that up specifically.
Is that in the Cal?
It's in the Cal
Okay.
response. Yeah, this is all thoroughly documented and described and discussed in the Cal response. And we'll be glad to get into much more detail with that with you.
Yeah, I think it's important to point out, we've been talking about, stability ratios of, first off, what's a stability ratio? We talked about stability ratios of 1.0. We've talked about stability ratios of 0.75. Stability ratio is a ratio of velocities. The critical velocity is the denominator, and then the modeled or calculated velocity in the numerator. So calculated over critical. Setting a criteria that we would only operate the plant in a condition with a 0.75 stability ratio actually puts in essence, 25% safety margin into your conclusion or into your calculation. So that's the difference between a 1.0 stability ratio and a 0.75. Traditionally, steam generators are designed originally coming out of the factory where you won't see tubes in conditions at greater than 0.75 stability ratio. We do know through industry practice and industry knowledge that as tube wear occurs, right, that those stability ratios can move up slightly, right? So that's why we took a look at the 1.0 stability ratio.
Right.
So, some of that's influenced by the contact force and other issues associated with the steam generator. So, just wanted to point out more for the audience specifically, we've been kind of a little fast and loose here on 0.75 versus 1.0 and stability ratio. Wanted to make sure people understood what we were talking about.
Thank you.
Thanks for that. So that would, just so I'm clear, but that's the whole purpose of calculating that stability ratio is to feed into the downstream models to calculate whether or not you have FEI in the out-of-plane direction. So does the Arriva work, the new work, also have new work that calculates the methodology for in-plane vibration determination?
the stability ratio is calculated for the restart of Unit 2 model in-plane vibration, not just out-of-plane vibration. So, by modifying the equation with the appropriate damping factors, we're analyzing against in-plane vibration. Again, one of the big lessons out of this, the old paradigm, and this truly is a paradigm shift in our opinion for the industry, the paradigm that if you had adequate margin out of plane, you were okay with in-plane, we analyzed against stability ratios for in-plane vibration, because that is the underlying phenomena that occurred.
Does the OA go into how this methodology, analytical methodology, based on the testing that was done, how that was qualified? And you said an expert panel, I guess, was involved in.
Yeah, the OA describes both the methodology and how the methodology was validated against measurements in the field.
Yes, and we had, Mr. Howe, we had the Electric Power Research Institute and their thermal hydraulic experts, as well as contracted thermal hydraulic experts through the Electric Power Research Institute, come in to challenge those operational assessments and their conclusions as well.
Yeah. And these companies who did the diverse methods challenged each other's work. So we had quite a bit of challenge, but fundamentally that methodology is thoroughly described, including how it was validated.
Okay.
Mr. Palmos, and I just want to, this may be oversimplifying this, but I think if I understand correctly, to clarify, you had essentially four different operational assessments. One of them you called the traditional. The wear rates that you use, though, although you're saying that's traditional and it's based upon the wear rates, it's the wear rates in Unit 3 that you used rather than in what you had in Unit 2,
correct? We took the severe case, which is Unit 3, which had significant wear after 11 months, and developed a wear rate correlation and applied that to the Unit 2 traditional operational assessment.
The other operational assessments, did they, can you explain, did they use the conditions that you believe were in Unit 3 or that were in Unit 2? Or
all the operational assessments took Unit 3 data to either develop the operational assessment methodology or to validate it.
Okay.
So it is all based, on the Unit 3 experience, and we factored that in, and the vendors factored that into their analysis of Unit 2. We felt the appropriate conservative thing to do, again, Unit 2 being susceptible, clearly a difference because of the support structure effectiveness, but taking the worst case data out of Unit 3 and modeling Unit 2 based on that data.
Was the support structure, though, in those assessments, was that the Unit 2 support structure modeled, or was it the Unit 3 support?
The Unit 2 support structure. So again, taking the Unit 3 data for wear and how fast it occurred and everything else we learned from Unit 3, when we do the operational assessment, we did many measurements in Unit 2 to characterize the support structure in terms of what the gaps are between tubes and supports, whether they're in contact, evidence of contact force, and developed a sophisticated statistical model to spread that over 10,000 tubes per steam generator and 12 contact points. So the Unit 2 support structure and tubes are actually modeled in the AREVA probabilistic assessment. The Unit 3 data is used in all the operational assessments in terms of wear rates.
Thank you.
Just one, maybe not final, but another line of questioning in this regard. So all this work, was this principally relied upon to demonstrate the acceptability of the AREVA work at operating at 70% power? I know it's a compilation of the other two, but in principle.
Principally the AREVA work. And two aspects to AREVA, one with a stability ratio of 0.75 and one with a stability ratio of 1.0, coupled with the 70% power.
So given that, do you all consider that a design change?
Well, I think if you think about the principle of an operational assessment, right? Principle of an operational assessment is to take known conditions either at your plant or at other plants, at other similarly designed and operating steam generators, and apply the wear rates seen in those steam generators to your conditions and predict the future, predict your operating period. So it's not a design change. The operational assessment process is intended, as the steam generator management program is developed through Electric Power Research Institute with NRC's involvement and endorsement, is that it is the forward-looking, probabilistic evaluation of what is the maximum safe operating period based solely on steam generator wear. So in essence, it is a prediction, right, a prediction of what's going to occur in the next operating period. So interestingly enough, and as we approach this, as Tom mentioned, the AREVA work is the backbone, operational assessment. But then we said, what if we're wrong? What if fluid elastic instability in plane begins in Unit 2 on day 1 of operation at the same rates it's been occurring on Unit 3? How long can the unit operate before a tube integrity issue becomes a concern? And that was the approach that we had a company by the name of Aptec take. The conclusions from that probabilistic evaluation, which again is very much in line with conventional operational assessment approaches, is that, what we mentioned in the last bullet on this slide that's up on the page is that these operational assessment predictions all showed safe operating periods in the 16 to 18 month range. Now, when we applied the additional 25% conservatism of the 0.75 stability ratio, it brought that predicted accepted time frame down into the 8-month period, recognizing that there's still 25% safety margin in that conclusion. Using the operational assessments is what plants in the industry have traditionally used for their proposed operating periods, following the discovery of a condition or a situation within their steam generators. That is the basis of the U.S. nuclear industry steam generator management program. Many plants in the past, in finding new situations or new occurrences in their steam generator, as the NRC, as you gentlemen are aware, have used the operational assessment process to predict safe operating periods. And then you go back into another period of inspection. The intention is to confirm the predictions of your operational assessments. In our cases, not trying to steal some of Tom's thunder here, but the last 2 bullets on this slide talk about that those operational assessment techniques predicted safe operating periods with conservatism and margin in them in the 16 to 18 month time period. Our proposed operating period is 5 months, right? So roughly 3 times or a third of what the safe predicted operating period is. And then we'll go back in and conduct a whole nother round of inspections to validate and confirm our conclusions and confirm the information that our operational assessments have predicted.
Thank you for that. And I understand that point of view, but I guess another point of view, and I'm not saying this is the agency view, is that, the anti-vibration bars were specifically designed to prevent FEI in the out-of-plane direction. Under the AREVA work, from one point of view, is that they're now being used to prevent FEI in the in-plane and out-of-plane direction, which is a new design function, some would argue. And so the question then becomes, how is that treated under your design processes, and how does that apply to the applicable NRC regulations that govern design?
I understand the line of thinking and understand that's, as you said, that's not necessarily the agency position. But the anti-vibration bars are designed to prevent excessive vibration, out-of-plane FEI, and at least by experience, also suffice to prevent in-plane FEI in the past.
That's right.
But by
So
operational experience, I grant you
Yeah,
that.
so it's not, in that sense, a change in design function.
Okay. All right, something we'll have to look at.
Yeah.
We understand it, and we're looking forward to having that dialogue. As Pete has summarized, the operational assessments conclude at 70% power, an acceptable operating period of 16 to 18 months prior to the next inspection, even with the very conservative 0.75 stability ratio, and there's more margin beyond the 25% that implies, a minimum of an 8-month period prior to the next inspection. Our proposed corrective action is to operate for only 5 months prior to shutting down and conducting an inspection, as Pete said, to confirm the effectiveness of our actions.
Tom, just to belabor this a little bit more, you did 4 operational assessments. One was traditional, and the other ones used some statistical analysis, some different assumptions. Can you just describe in layman's terms the operational assessment that you actually used, what you compiled together, kind of the assumptions, basis of that?
Fundamentally, again, it's all thoroughly described in the CAL submittal. We'll be glad to get into deep, but fundamentally, as we've said, the backbone is the AREVA work, and the AREVA work had 2 aspects. One was an assessment of stability ratios crediting no supports, assuming the support structure is not effective at damping, with a stability ratio of 1.0, which demonstrated at 70%, we would have an operating period prior to the next inspection of 16, 18 months. So the stability ratio calculation is based on the thermal hydraulics, principally, okay?
So essentially that was saying you could operate for a period of time without FEI occurring. Is that
Without FEI occurring.
the assumption?
Not